So homework, the project 2 is due today. Project 3 will be given out by Thursday, and that will be due by the end of the semester, just before the end of the semester. And then you will have to set up a time at that time. Everybody gets like a 15-minute slot with the DA to show their entire system working. So in case you are making this stuff up without actually writing any programs, you still have to show an actual running program by the end. And the plus point of that is, in some sense, you get partial credit for pieces that may not have been working when it was due, but you still made it work by the end. You will get some credit for that. Okay, because in essence we split the credit across these three as well as the demo. So yeah.
So if it was working at the submission, then we broke it.
Then you get a really good present for Sushoma, who is going to check the demo. So yeah. Okay, so that's the deal regarding the project. Are there any questions? Okay, if not, then it's as good a time as any to start the discussion that we were in the middle of last class. By the way, I think I gave the homework problems for these parts. Okay. So we were talking last class about computing the probabilities for the naive classifier, which is really one of the nice things, actually. In fact, the fact that you can do this, you can compute probabilities this way, just in terms of counts, I didn't prove it to you. It turns out that you can prove that that is the right thing to do by essentially computing an expression for the likelihood of the data given the naive classifier. So for example, so you have the naive classifier, remember class C, causes, attribute A1, A2, etc. Now, if this is the naive classifier, it was generating the data, okay, then if I have seen a huge number of training examples, let's say 100 training examples, for each of those training examples, you can compute what is the likelihood that that example would have been produced by a naive classifier. Okay, that would be, for example, suppose I said this whole thing. Let's say, suppose I'm considering this example right here. Let's say this corresponds to the class S. So now, if I know the MVC, then there will be a probability P with respect to which class would be yes, and 1 minus P, that class would be no. So I would have picked the class yes, so that means I've picked it with probability P now already. Then if I pick that class, then the probability that A1, let's say what is A1 for us, that is alternative. So if class is P, if class is, if you're actually waiting at the restaurant, the probability that the restaurant would have an alternative. Okay, so there are two probabilities that you're going to store here. Probability that you have an alternative given class is C, and probability that you have an alternative given that class is not C. Okay, you don't need this other number, probability not A given C, because P A given C plus P not A given C must be equal to 1. Right? So these are the two numbers you would be remembering, right? And these are the two probabilities that are present in this particular table. And what you can get is, for an entire example, you will get some expression of the type P times P1 times P3 times, so P11 times P3 2 times, where P11 means attribute A is taking value 1, okay, and so on. Okay, so some sum of probabilities, some multiplication of probabilities. Okay, now this one more example independently generated that do have multiplication of probabilities. So what you will then have is the total likelihood that all these examples would have been generated would be the multiplications of these products. Okay, and since it's a huge big multiplication, you can take a logarithm and it will become sum. Okay, and that essentially is called what's called the likelihood of the data given the classifier. And what you're trying to compute is the specific classifier that will maximize the likelihood. So the data you see, you want to learn a network which would maximize the probability that you would see this data. So what you get in this kind of a scenario is a likelihood expression, which is, you would actually get it in terms of products of probabilities. But if you take, you can, and what you're trying to do is maximize it. So look for the values of these probabilities such that this expression becomes maximum. This full product becomes maximum. And these are continuous values, right? So the last time you thought of maximizing a function was in calculus, where you would essentially, to maximize the function, you take the derivative and equate it to 0 and see what the values are. In this case, there are multiple variables. The probability here, the probabilities here, and so on. And for each of them, essentially, you will get a partial derivative and you equate it to 0. And then that will tell you what is the optimum value. What's the value of these parameters where the likelihood would be maximized. And it so happens that if you were to go through that whole thing, then you will realize that the place where it will be maximized is these counts, which is what your intuition told you. But intuition is not the reason we actually do this. In this class, I just tell you, you can do this. But if you were to take learning based networks or statistical learning, then you will realize that the whole point of statistical learning is to set up a likelihood expression for the data and maximize it. Now, normally, if you maximize the product, the place where that becomes maximum is also the place where the logarithm of the product becomes maximum. Because logarithm turns out to be monotonically connected to any function. If a function is increasing, so does logarithm, right? So if I'm trying to find where f of x becomes maximum, I can always take log of f of x and see where that becomes maximum. And it's useful to take logarithms in these cases because then all of these become a whole bunch of summations. And one of the most beautiful things here, and this is something that you couldn't care less about right now, but once you start thinking about statistical learning, one of the most nicest things about Bayes and in general Bayes networks is that this likelihood expression splits into individual parameters. So if you have, k parameters, k different probabilities you need, you will get k different equations, each of which will give the value of one of the parameters. That's why it almost looks like learning is like a no-brainer here. You don't feel as if you're doing any learning here. You just counted the numerator divided by the denominator. But actually it is learning. It just so happens that for the Bayes networks, it has this beautiful property. Okay, in many, many cases this property doesn't hold, and in fact you have to do function optimization. So as part of learning, you will actually try to do gradient descent or something to find the minimum or the maximum. So that's the connection as to why Bayes classifier becomes easy. It's because it's Bayes networks, and when you have Bayes networks with complete training data, that means all the attribute values are given to you, then this likelihood can actually be split into the parts that correspond to each of the, so it gets decoupled such that one equation for each of the parameters. You don't even have to solve, you do not even have to solve simultaneous equations. And you certainly don't have to solve nonlinear equations. Do you see what I'm saying? In general, if I just give an arbitrary function and say, find the place where its gradient becomes 0, the gradient could be a nonlinear function. And when you equate it to 0, you will now have to solve this nonlinear function equal to 0 and find the zeros of this nonlinear function. You didn't have to do it here. Okay? So in some sense, I want you to understand that this was just a happy case where it turns out to be extremely easy. You can just think that this is the way, you might think by looking at this that all learning is like this, but it just happens that for this particular case and a few cases like this, the probabilities can be computed just by taking the counts. Okay. But the other thing that I pointed out is that you might have training data might be biased, because of which you might actually have to, the probabilities that you are estimating from the training data might not have been the probabilities you would have gotten if you had bigger training data. If it wasn't too biased. Okay, so this is why, actually the quote for this essentially is, it says, I beseech you in the bowels of Christ, think it possible that you may be mistaken. Okay, that's exactly what you're trying to do in smoothing. Okay, so you suppose are trying to find what's the probability that this attribute will have this value given that your class is this, right? And then you looked at the data, and for that particular class, no example has this attribute with this value. Then you'll get 0 divided by something. So you would say it is 0. The moment you say it's 0, then there are two issues. First of all, you committed to actual probability, just based on a few examples. And second of all, because you're going to multiply probabilities, right? Then if you get 1 0, then everything else becomes 0. Okay, so you then want to do smoothing where you essentially, as I said last time, sort of assume that the training data you are seeing is just the tip of the last K. Let's say you're looking at 100 training examples, you assume that these are the last 100. Before that, you have seen maybe 1,000 virtual samples. And you have some experience about these samples. Okay, so the M is the number of virtual samples. And then the question would be, how many of those virtual samples would have had AI equal to VI? And then that is your prior on how do attributes take values in that class. And if you don't know anything, you can assume uniform probability. Okay? So then that way you would essentially be adding something to the numerator, something to the denominator, and that sort of smooths the probability. And as the number of training examples really, really increases, it does not matter that you assume that there was a bunch of virtual samples to begin with. But in the beginning, it actually makes sure that you are not too biased by the training samples you got. That's exactly what this is doing. Now, in the text case, we'll see in a minute that the usual way you do this for the text case is this would be in terms of words. You would be considering probability that you will have a particular word in the document, given that it's spam mail. That's the kind of probabilities you're trying to compute. That would basically be in terms of the number of times this word occurs in the spam mails, divided by the total number of times this word occurs. Right? That's what you would be doing. Total number of times it occurs in the spam mails divided by the total number of words in the spam mails. Okay, and the only question then is that you want to make sure that you smooth the probability. To smooth the probability, you essentially assume that you make, just to make life simple, you assume that you would make cardinality of V being the vocabulary. Let's say the vocabulary is 1 million words. So you'll assume that there are 1 million virtual samples. And you'll assume that each word in that sample occurs with the prior probability of 1 over V. So if you do this, then in the bottom you would have, the number plus V, and the top you would have V times 1 by V, which will be 1. So the effect would be adding a 1 to the top and adding a capital V to the bottom. Okay, so that's the way the smoothing is done in the text case. But we'll see it in a minute, more detail. Okay, that's what it is. The second thing that you want to remember is, since you're going to be doing in knife-based classification, you're going to be multiplying a whole bunch of probabilities. And so you're likely to get underflow errors for your machine. You basically are multiplying a huge number of probabilities, all of which are probabilities are obviously less than 1. Okay? And so to avoid underflow errors, it's typically people just take logarithms of all the probabilities and add them. It's a very useful thing to do. That's the same thing that I was doing here. Even in optimizing the log likelihood, instead of optimizing the likelihood, I optimize the log likelihood and realize that when log likelihood becomes maximum, that's exactly the place where likelihood also becomes maximum. Okay, so that's the other thing you want to remember about naive-Bayes classification. Now, let me just go through naive-Bayes classification just for text. So now you understood why naive-Bayes classification works for a general case. And if you just think in terms of text, so here's what you want to think of. So suppose that there are words from a fixed vocabulary V that appear in each document. And each document has some class, maybe span, not span. This is an article from this news group, this is an article from this other news group, and so on. Okay, so now what I remember that all I need to compute is this probability of example given class. That's what I need to compute. So for us, examples are documents, so probability of document given class. So I will first assume that the simplest thing to assume is the document is nothing but the words in the various positions of the document. So up front, I will start with the correct, no assumptions. Here I'll say probability D given C is nothing but probability that word 1 occurs in position 1 plus word 2 occurs in position 2, word 3 occurs in position 3, and so on, all the way to the end of all the positions in the document. Given that it is class C, the document happens to have class C. So this is kind of saying, if in fact this is a span mail, the probability that the word da occurs as the first word, the probability that the word Viagra occurs as the second word, the probability that is occurs as the third word, and so on. Okay, right? Now remember, this document is maybe 1,000, 10,000 words. Okay, and so you essentially have this 10,000 length joint probability. 10,000 length joint probability. Okay, and obviously you are not going to be able to compute this probability directly. Instead, you make this huge assumption that first of all, that the words are all appearing independently in their positions. That's the first independence assumption. Okay, if they're appearing independently, then this joint probability can be written as probability that word 1 occurs in position 1 times that word 2 occurs in position 2 times word 3 occurs in position 3, and so on. Okay, we're still not out of the woods. We still are saying each word now has to have a probability. Given a class, let's say spam and non-spam, for each word I need to know now what's the probability that it occurs in the position 1? What's the probability that it occurs in the position 2? What's the probability that it occurs in the position 55, 2009, and so on? Okay, right? So if you have two classes, and if there are 10,000 positions that you're considering in the largest document, okay, and you have V words, which is the number of vocabulary, okay, then you essentially wind up needing 2 times 10K times V probabilities, which is still significantly better than 2 times 10K power, so V power 10K, which is what you would get. Is what you would have needed if you are trying to use these as the probabilities. Okay, I'll make one more assumption, and I'll assume that the probability of a word occurring in the document is independent of the position it occurs in. All right, we're sunk already. We're already assuming that words occur independently. So why not go one more level and say word occurring in the first position is the same probability as it occurring in the 15th position. So you just, that way you can just talk about word occurring in the document as against word occurring in a particular position. So I will make that additional assumption. So probability that word occurrence probability is independent of its position in the document. That's what the second assumption we are making. If I do this, then the 10K will go away. So I just need 2 times V. Instead of 2, of course, the number of classes times the vocabulary. For each word, I need to know what is the probability that it occurs in a document belonging to that class. So I would need these many probabilities. It's a huge number of probabilities, but remember that these probabilities are just a bunch of, ratios, right? Okay, and the last thing, of course, is I want to talk about the smoothing. Right, I basically, so if I'm thinking in terms of these many probabilities, C times B probabilities, then for each probability, basically I would just be asking what is the probability that word W occurs in class C equal to span, let's say. Word equal to Viagra occurs in class equal to span. Okay, and that would essentially be the number of words, number of times this word is occurring in this class divided by the total number of words in that class. So the relative frequency of this word in this class. Okay, I want to then, so that's basically what, forget about this 1 and this V. So I'm just saying, what is the total number of words, total number of times WK is occurring in CI? So let's say there are 15 span mails. In the first one, the word WK is occurring 10 times. Second one, 10 more times. Third one, 5 times, and so on. You add them all up, and you get the number of occurrences of this word in that class. Divided by, this is just the total number of words in the class. So you concatenate all the documents of this class into one document, count up all the words. That would be the number of words in the class. This tells you how often is this word occurring in this class, essentially. Okay, now I'm just going to change this a little bit in terms of smoothing by adding a V here in the denominator and adding a 1 in the numerator. That is basically now going to say that I have extra V virtual samples. V being the size of the vocabulary. Okay, and then each word, in those virtual samples, each word occurs with probability 1 over V. So if I do that, then this would be this plus 1 divided by this plus V. The practical implication of this is no word has probability 0 of occurring in any class. Because you always have a 1 on the top, so no word have a probability 0 of occurring in any class. Okay. The other issue, of course, is that you will be less biased by just the training samples. This is what you do. This is all you do for computing the. So you'll remember these probabilities, and once you remember these probabilities, next when you get a new document, you can then compute its class by computing the products of the probabilities and see which one winds up being bigger, as we saw last time. Okay. So, and in fact, this one is just an example. So it was used to classify Usenet articles, let's say, long back, from 20 different groups, and it's able to achieve an accuracy of 89%, which is pretty astounding because if you have 20 different groups and you just randomly choose, then the probability that you are correct is only 1 over 20, 5%. But naive-Bayes classifier was already able to get you up to 89% probability of correct classification. A very simple idea. Okay, this is why it gets used a lot in text documents, text data classification. So this slide and the next slide actually are just showing you the training phase and the testing phase for the naive-Bayes classification. I already said that, but it's just separately put into 2 different slides. So for the training phase, you assume that the V is the vocabulary. For each category C, you sort of consider the subset of documents that are in category C, and then you compute the number of times. So to get the class probability, you just basically take the size of this document. So it's actually easier to think of bags, right? Each document is a bag. Okay. So DI is the bag of the class I. It's a union of all the bags, which is another big bag. And D is the union of bags of the original set of documents. So you compute the DI by D, that will give you the class probability. Okay? And then basically to check the probability that word J given class I. Notice you no longer talk about position, right? Because we assume the word occurs in every position with the same probability. So what's the probability that word J occurs in class I? That is nothing but the number of times the word J occurs in class I documents together plus 1 for that smoothing factor, divided by the total number of words in all the documents of class I plus V. These are huge numbers we are talking about. Okay? I mean, in the homework example, I give you small documents of size 3 words or so, and a total vocabulary of size 5 or something. But you know, normally you just have to assume a large vocabulary and the unlimited size of the documents. I mean, indefinite size of the documents. So you just remember this. You compute these documents, these probabilities, and you store them away. For each word, you have a probability for each class. That's what you learn. And given a new document, what you need to do is compute this expression for each class. This expression for each class, where it's essentially saying the probability. So this is where AI is the word occurring in X. So you're computing the probability of words occurring in this document. Okay. You assume that it's class CI, so if it is class CI, then this is the prior probability of class CI times these probabilities of all the word occurrences, and then this will give you a number. Whichever class has the highest this number, that is the class you will give this document. Okay? So that's basically naive-Bayes classification. Okay. One thing that I want to talk about now is, since we are actually talking about text, one of the issues, and this is true for general machine learning, but it's particularly true for text classification, which is that this is too many words in documents. Most of these words are probably irrelevant for the class of the document. The word is obviously is not very important, right? And in particular, the reason you think the word is not important is because is present in both spam mails and non-spam mails. The reason you think Viagra or Nigeria are important for spam classification is because you assume that there is more instances of Nigeria and Viagra in the spam mails than in non-spam mails. Okay, so what I really want to do is figure out which words are really worth doing all this calculation for. So before I actually do the naive-Bayes classification, I want to first select the words that are indicative and only focus on them. So suppose the total number of words in all the documents together, total number of distinct words in all the documents together that you have is, let's say, it's 10,000. Suppose I only want to remember 1,000 probabilities. I mean, probabilities for 1,000 words. So 1,000 words times each number of classes. Then the question is, which 1,000 words should I remember? That's the question. And that's the feature selection problem. So you're actually selecting the words over which you're going to learn. So it's like a learning before learning. Do you understand what I'm saying? So for example, I'm trying to predict whether or what grade you're going to get in the class, let's say. Okay? And then there are so many features about you. And up front, I might just say, well, the t-shirt you are wearing is irrelevant. So I'll remove the clothing features. I'll remove the length of hair features. And I'll keep maybe your GRE score and maybe your midterm score. Maybe your homework score and so on. So I kept some scores, but some features, and removed a whole bunch of features. By doing that, in essence, now I have a smaller learning problem where only I'm going to be learning with respect to these relevant features. It's very useful to be able to do this. Okay? The question, of course, is how do I figure out relevant features faster? Okay? In fact, the whole area of feature selection is sort of like dimensionality reduction. This is also like dimensionality reduction, where basically you might have started with 10,000 dimensions, but then you sort of did like a LSI, and you found that the effective dimensionality of this data is like approximately 7. Because after 7, the variance you are losing is much less. Except in the case of dimensionality reduction, the features that you pick, the axes that you pick, have no obvious connection to the original axis. Because each axis would be some arbitrary linear combination of the words in the previous. In feature selection, the assumption is you're only picking some of the features from the original space. So in some sense, feature selection is a specialized case of dimensionality reduction. Dimensional reduction, you're actually looking for some linear combinations of features that are the most relevant indicators of the class. Okay? Here you're just picking which of the coordinates are more important. You know, here's a 10,000 coordinate document, a coordinate point, and you're saying coordinate x7, x15, x95 are important, the rest are not. And it may well be that actually they are not they're not important all by individually. What you really care is x3 plus x17 plus x97 divided by 4. That's the feature that you really care about. In which case dimensional reduction would have found that for you. So it will further reduce the dimension. But feature selection is worth thinking about because essentially it's like an easier problem. You're just picking which coordinates are more important. Okay. So one very interesting idea, one very simple idea is here. So feature selection is a whole area. Okay, feature selection is sort of pre-machine learning. Before you start learning, you want to select the features over which you want to learn. Okay. Now, of course, the features that you select have to be connected to what you're trying to learn. So, for example, if instead of predicting your grade, if I'm trying to predict which of you are going to win the Mr. Tempe, Miss Tempe, beauty competition, then your midterm grade is completely useless. Maybe it is actually negatively correlated, but that's a different story. Okay, so mostly it's irrelevant, right? Right? And what does matter is the length of hair and the color of your t-shirts, your fashion sense, all those things. Okay, so this is actually an important point. Feature selection, unlike the LSI which we looked at, where we assumed somehow the class is not important, okay, feature selection is done with respect to class. So in fact, that's why I mentioned last class that LDA, which is the linear discriminant analysis, which is a general case of LSI, which does take class into account and does dimensional reduction. Okay, but anyway, coming back here, what I'm really interested in essentially is how are the features and the classes distributed over the examples. So think about this. Okay, here are all the examples in the world. Here are all the students in the world. Okay, and then some oracle that I don't know has already predestined the grades that they were going to get. Okay, so they're sort of distributed randomly. Random doesn't mean uniform random, by the way. First remember this. Random doesn't mean uniform random. Okay, so with some distribution, they sprinkled A, B, C, D grades over these kids, these students. Now, with some other distribution, they sprinkled their fashion sense. Some yet another distribution, they sprinkled their midterm scores. The question I have is if the distribution with which they sprinkled the midterm scores, is it correlated with the distribution with which they sprinkled the grades? If they are completely independent, it doesn't matter. If it's correlated, either positively or negatively, it matters. Do you understand what I'm saying? So it is true that some of the people who are getting eventual A grade in this class have a great fashion sense. Okay? But that doesn't necessarily mean, in fact, if fashion sense is completely irrelevant, then it is important that there are some people with good fashion sense who get good grades. If everybody with no fashion sense gets good grades, then in some sense it's a predictive feature. You should start losing fashion sense to get good grades. Right? So again, remember, independently, when you put these things independently, then there is a probability that they will be together. But that probability would be just given in terms of P of A times P of B. So in particular, I'm interested in finding out what is the joint probability of this feature and this class occurring together, divided by the class occurring, the class occurring together, class occurring by itself, feature occurring by itself, class occurring by itself. So I'm trying to compute, in essence, to see whether A is correlated with B. I'm taking P of AB by P of A times P of B. Now, if they are independent, this would be P of A times P of B, this would be P of A times P of B, so they'll become 1. If they're dependent, then it will be anything other than 1. Right? Okay? So, in particular, So then what I will do is I'll take a log of this. If I were to take a log of this factor will become exactly 0 when they're independent. Which is basically, independence is the most useless thing about a feature. If the feature is independent with respect to the class, then it's not a relevant feature for you at all. So it should basically, somehow you should get a 0 there. Okay? So I'll take log of that. And then now for each class, okay, so if I have spam and not spam classes, then I would be computing what is the probability of Viagra and not spam by probability of Viagra and probability of not spam. And I'll also compute one more component, which is probability of Viagra and spam divided by probability of Viagra and probability of spam. Right? There are two of them. Now I need to combine these probabilities, so I combine them in the weighted way. So I would essentially say probability of spam is a probability of Viagra and spam times log of that probability, plus probability of Viagra and not spam times the other probability. Do you see what I'm saying? So the interesting thing is that in a multi-class classification in particular, it could well be that a particular word is independent with respect to one of the classes, but it is dependent with respect to some other class. Do you see what I'm saying? So that's why you essentially have to consider this expected correlation. This is sort of an expected correlation. And you sum over all the possible values of the values that feature can take and all the possible values the class can take. And if you do this, you'll get a score. And that score you can think of essentially as how correlated is this word to the actual classification task you have on hand. Okay? And the higher that score, the better the word. So you can compute this score for every word, sort them from the top to bottom, and take the top 1,000. That's the way you can get the 1,000 most relevant words. Okay? And then when you do that, you then essentially can just do naive-Bayes classification only on those 1,000 words. So it's as if the rest of the words don't exist in the document. You only care about the occurrence of these most important words. Okay? So here is this is Wanlu, because Wanlu actually, in fact, half of his life, most of his life, he was doing feature selection. That was actually his area. Okay? And this is sort of the simplest idea in feature selection. One interesting idea that you might think of, which in terms of extensions, is something that Wanlu and his students did, actually, is this, which is sort of, suppose you pick the most correlated feature first. The second feature you pick, should it be the second most correlated feature? And when did I ask a question like this before? If you pick what? What? Secondary eigenvalue? No. Diversity. So that can be whatever, I don't know. So the point is, the first, if you're showing the top 10 results, the first document should be the most similar document to the query. The second document should not just be the one that is the second most similar to the query, it should also be the one that's the farthest from the first document. Otherwise, you can just keep giving copies of the same document multiple times. Right? Diversity is important. But it's true for the words too. Suppose it turns out that data and structure are essentially, it's like a phrase. So whenever data occurs, structure will occur anyway. So if data has high correlation, so does structure with your class. Then why should you take both of them? If you're only going to take two words, taking data and structure basically is taking, you're losing one of your bullets. Do you see what I'm saying? So then to be able to catch that, you need to not only compute mutual information, this is called mutual information by the way, Okay, mutual information between, in this case, you are computing a mutual information between the word and the class. Okay, but you also want to compute mutual information between this word and the previous word. Okay, and you want to reduce that. Right? Because if this other, given the other word, if this word is highly correlated with the previous word, you don't want this word. So you sort of penalize it. The second word would now be, after picking the word with the highest mutual information, the second word would then be picked as its mutual information with respect to class minus its mutual information with respect to the word that's already been picked. If you do this, you are diversifying. You are essentially ensuring that the features you are picking have less correlation between each other. Okay, and this is completely connected to the idea of picking the second document to be something that's not only most similar, second most similar to the query, but also is farthest from the first document. Okay, so that if there are two documents, one of which is basically a carbon copy of the first document. I can't say carbon copy because I don't think anybody knows carbon copies anymore. You know, it's a copy of the first document. And here is another document. It's completely different. And this one is 0.93 similar to the query. This one is 0.97 similar. You may still decide to take this because this one is farther from the first result you get. Okay, that's a great idea. Right? And in fact, that's something that one of the students here, you know, did this with one some 5 years back. Okay. So again, this whole area is feature selection. You know, that's what he does. One of these things. Okay. This is a worked out example. I've been writing this with respect to spam and Viagra here, right? Okay. Here is a worked out example for computing mutual information with respect to the class. So in this case, a class is poultry versus not poultry. And the word that I'm using is, word I'm considering is export, and export is present, export is not present. Okay, and then these are, and of all the documents that I have, I essentially split them into these 4 cases. The class is poultry and the word is present. There are 49 such cases. And class is poultry, the word is not present. That's 141 cases. Class is not poultry, the word is present. 27,000 cases. Class is not poultry and the word is not present. That's 774,000 cases. So then, you know, this expression tells you how to compute the mutual information. So if you have any questions, look at this. That's what I was saying. Okay? And this is not, I mean, it looks ugly on the board, but it's a very simple calculation if you have the numbers. Okay? So it's a very cheap thing to compute. This is a very cheap feature selection method. And this picture just shows you, this one example of many, that if you were to select features, versus not selecting features, then knife-based classification does better. Okay? I don't quite remember which is which. So here is the number of features selected. So in essence, you notice that if you select too many features, the F measure is falling down. F measure is precision recall combination. Okay, if you select too few, it's low. Select too many, it's low again. Because in this case, you overfit. Okay, and then in between is when you wind up doing the best performance. Do you understand what I'm saying? So again, this is on the test data. So if you were to learn your knife-based classifier on all 50,000 words in the vocabulary, not only would you take more time, but you will actually do worse during the testing. Because the chance that you fixated on an irrelevant feature is very high. Fixated on an irrelevant feature is very high. Okay, this is a classic thing. So suppose I just am looking for every possible feature, then it turns out that, you know, in my training example, there was this one kid who is wearing a very particular red shirt, you know, with blue cap. And he got an A, he or she got an A. Okay, now then I'll just assume that, well, obviously it's extremely well correlated. So I will just start thinking that somehow explains getting A. And before you start laughing at it, think about the fact that human history is full of fake hypotheses like this. Completely fake hypotheses like this. We will come up with some random hypothesis and we'll move on for a long time saying the Earth is in the center, everything else is revolving around it. I have this great hypothesis, I don't need to check it. And we are always full of these kinds of things. Okay? So the overfitting is a problem, and so in fact, figuring out what are relevant and irrelevant features does reduce also the overfitting problem. In some sense, what I said here is also can be said for dimensionality reduction. Okay? And latent semantic indexing is something that we talked about before, and this basically is just summarizing what I already said today's class about the connection between feature selection and dimensionality reduction. Okay? And also the connection between dimensionality reduction when there is no classification involved. In a sense, you just want to maximize the variance across the dimensions. Versus when the classification is involved, in which case what you want to capture is the variance with respect to the class, not variance just by itself. So that was this picture I was telling you. So if I give you a data like this, if you do LSI, you would assume this is the primary feature, and that is the secondary feature. But if I tell you these are all spam mails, these are all non-spam mails, then all of a sudden the most important feature is that. In this case, at least, the most important feature happened to be perpendicular to this. But in some other case, it may have no connection to the origin, the LSI features. Okay? And this is called LDA. Actually taking the class information into account while doing dimensionality reduction is called LDA. Okay? Any questions? Okay. I will just, so this basically is something that I mentioned long back, I think 2 classes back, about the fact as to why naive-based classification, which makes all these crazy assumptions, still does work well in practice. And the reason it works well is because even if it is bad in computing the probability, if the relative order of the class probabilities is correct, then it still wins. Okay? So that's basically the explanation for that. So that's on the text classification, and what I'm going to do is change gears a little bit, not too much, and go into recommendation systems. It turns out recommendation systems really are, you know recommendation systems, every site you go to recommend stuff to you. You say, buy this book, you would be interested in this movie, or something else, or you may be interested in this news article. They're all trying to recommend you. Okay, now obviously that's a classification problem. Okay, so they need training data first of all. Okay, about your likes and dislikes, and then somehow use that training data to classify new books into things that you would like and things that you won't like. And if the book has high probability of you liking it, then they should suggest it. Okay. So it's a classification problem, and in some sense, there are two broad ways in which the recommendation systems work. One is what's called content-based recommendation systems, where in essence it keeps track of your likes and dislikes based on things that you bought, for example. And then just based on that, it tries to learn a classifier system, say which books you might like later, and then present them to you. Okay? So it's completely customized to you. In the other case, you do not care about, so to be able to do content-based recommendation systems, for each book you buy, they essentially, so let me go skip a bit and, okay. So content-based recommendation systems are basically, this is nothing but what we have just done till now. It's just classification task. So the idea is every item that you have shown that you like it, either because, and there are multiple ways users can show that they like an item. Okay, and that's what this slide is about. You need first feedback, just as we talked about the fact that in the classification task, the biggest problem is having labeled examples. In recommendation systems, what is labeled example? Saying the books that you like and the books that you don't like. Okay, now how do you tell me the books that you like versus not like? So you may not ever sit down and tell me what you like and not like. Instead, you just would be doing your thing and I have to follow you along. I, the system, have to look at the fact that you look longingly at some book. You know, that's why, in fact, Amazon has all these things like wish list. You know, I wish I had money to buy this, so I will take the time to put the book in the wish list. That's what?
That's intrusive.
Which one?
That one is semi-intrusive, the wish list.
Intrusive, you mean?
Semi-intrusive.
Everything is intrusive. That's a very different story. I mean, they also want to send this wish list, I guess, to your friend saying, this poor guy wants the book and his birthday is coming. You know, don't be a cruel person, please buy it for him. It's just nothing, you know, we're just being, you know, good Samaritans. Not that we'll make any profit or something because you give this book to him. But anyway, so in this case, in the non-intrusive cases, to some extent, you don't ask the user. By the way, the word intrusive here is, are you specifically asking the user to label the examples or not? I think the point you are making is intrusive in terms of privacy intrusiveness, maybe. Okay, so here, if I printed a page, you know, a book page, okay, or if I put it in a wish list, or if I actually bought it, then I'm indirectly telling Amazon that I like this book. Unless I'm one of these crazy coots who buys 1 million copies of that book and just basically throws them out because, you know, there's some bad damning information about you. In fact, recently there was a case where New York Times had this article about a small town newspaper whose day-to-day circulation is about, you know, 1,000 copies, and on one particular day they ran out of 2,000 copies that they printed. Okay, why? Because they had some, you know, in this small town, they had politics about some particular guy, you know, some doctor kind of overcharging patients or something, and they wrote this local story. And so the doctor and his kids woke up early in the morning and bought every possible copy of that paper. Okay, not to frame them and keep them, just to stop you from getting it, right? So, except in those crazy cases when you buy something, it's because you like it, not because you hate it, right? So all of these you're doing yourself anyway, and then basically you are indirectly giving a label to the book, label to the item. Okay, and then the intrusive is you can ask people to sort of directly say whether or not they like this book. Okay, and there could be in between, which is you sort of present to users books that you think they might like, just so that you can see them putting them in the wish list. In which case you got, so you almost sort of got them to label data for you. When they weren't planning to label the data, but you know, if the thing is good enough, then you are likely to click on that book and look at what is in it. And then the underlying learner can say, bingo, we now know that in fact our learning system is good in this case. Okay, so those are the ways you get the labeling. If you have got the labels, then the question is how do you use them? There's one way of using them which is content-based, where you would then essentially describe each item that you like in terms of some features. So books have to be described in terms of features. And if you're buying an electronics item, they have to be described in terms of features. So the attributes and their values. Okay? And if I have attributes and their values and the class for the training example, I can do naive-Bayes classification. Right? Okay. So the only question is that I do need to be able to do content-based, sorry, this is not the right slide, but to be able to do content-based classification, I need a description of each of the items in some feature space. Okay? And we will also, so let's look at that first. And then, so for example, if I'm doing books, right? Books, basically the title information of the book, the cost information of the book, the reviews information of the book. These are all features of the book. Okay? So what you can do, actually what Amazon can do in this case, and probably this is what they do, I can't be sure, is they can do naive-Bayes classification, but a slight twist. a word occurring in the title might have a different meaning than the same word occurring in the reviews. Okay, cheap and fast as a title is good. Cheap in the review is not very good. Do you see what I'm saying? For the same book. Okay, so what you might want to think of is, yes, book is, the page that Amazon is showing you for each book. That's a bunch of textual information about the book. Forget about pictures. There's a bunch of textual information about the book. Instead of just assuming all of that is one single bag of words, you might think of that as a vector of bags. The vector has fields, so there's a title field, and that's a bunch of words. There's a review field, that's a bunch of words. There is the price field, that's a bunch of words, and so on. Okay, then what you can do is you can compute the null-based classifier, okay, not just with respect to the class, but with respect to the word occurring given the class and the vector field. So what's the probability that the word cheap occurs in the books you like in the title of the book? Or what's the probability that the word cheap occurs in the books you like but in the reviews of the book? Or the word cheap occurs not in the reviews but in the price? Each of these are different, they have different sense. So you train your null-based classifier now, not only in terms of the number of words times the number of classifiers, but number of words times number of classes times the number of vectors in each class, and number of fields in each class. Sorry, number of fields in each item. Okay, so if the book has the title field and the price field and the reviews field, and that's, let's say, and then the reviews field can be, let's say, the unsolicited reviews field, which is the user's writing, and the publisher's review field, which is the published reviews. So then you compute these probabilities for the word and the class with respect to each of these fields. You have more probabilities now. But then, that's a little more costly, but then you can actually do a better classification of the book. Okay? And furthermore, so now when you do this, so if you have a bunch of books that I have bought, then I compute these probabilities for the class probability as well as the word for class and the field probabilities. That's what I store as the profile of the user. And when a new book comes, I use these numbers to compute this expression. And if this expression is above a certain threshold, then I'll say, yeah, I think you like this book. If it's more likely that you like the book than not like it, I will recommend it. Okay? Right? That's basically the way you can be doing recommendation. And that's actually, a lot of recommendation systems work like that. It's a very cheap thing to do. It's null-based classification again. Okay. So the other thing you can do actually is that if I want to recommend, there is another thing that I skipped, which is if you were to recommend to people something, oftentimes they would like to know, why did you recommend it to me? Not always, but sometimes. You want to know, why did they recommend it to you? Now, one advantage of content-based recommendation systems is when I do recommend it to you, I can give you a reason which you might understand. You might say, you seem to be the cheap kind of a guy. You bought every book that has the word cheap in it. Or you seem to be a math kind of a guy. You bought every book that is sort of class mathematics. So that's why I'm showing it to you. Moreover, they can actually just say, instead of that, they can show me the words that are important in making this decision for me. Or they can just show me the examples that best exemplify the previous books that I have bought that best exemplify this, and say, you bought this book and this book and this book, so we think you will be interested in it. Then you will at least say, yeah, I can understand why you think so. Okay, so justification is possible for content-based systems. Okay? That's content-based systems. And so, by the way, one of the interesting questions here, what you're doing here is, if you can actually pick up all the words, you have a whole bunch of words and their connection to the class as well as the field. But if I'm showing you the most important words in this book that must be relevant to you as to why I recommended this book to you, then you sort of need to pick those books, I mean, those words that are like the most, that have the highest probabilities